Hello, we are Literature Review Group 4, and today our group is here to discuss ingestible medical devices and their recent developments of this growing field. Our team is comprised of electrical, biomedical, and industrial engineers, and we have all come together to apply our skills to investigate this significant technology. Historically, sensors have been an active area of research, but recently there have been enormous amounts of developments, all ranging in different applications such as diagnosis of disease, body cavity temperature and pH data collection, and much more. The use of ingestible devices in commercial medical industry is still in its infancy. Our team is investigating this topic in detail by focusing on target biomarkers within the body, device connectivity, and novel materials. These are the three key areas of improvement and research in this field. Although ingestible medical devices are still not a common technology utilized in medical practices, they have enormous benefits. Common techniques used for data collection and diagnosis are time exhaustive and costly for the patient and the practitioner. The implementation of these devices over time would allow medical practitioners and researchers to have access to detailed diagnostic information more efficiently.
As a recently emerging technology, orally ingestible devices have recently evolved to incorporate different biomarkers that can be used to aid in both diagnosing and treating various ailments. These biomarkers have been predominantly discovered along the gastrointestinal tract and have been linked back to physical health conditions. Common biomarkers include intestinal gases, blood, and molecules. These biomarkers are traditionally collected through common methods like endoscopy, breath testing, and stool analyses. But in order to obtain accurate measurements of these biomarkers, the measurements must be taken from inside the body, which leads to the more invasive method of endoscopy being used. And as you can imagine, cannot be very fun for the patient. It can typically be very time consuming. But ingestible devices allow for the collection of these biomarkers in a more time efficient manner without discomfort to the patient. And as I mentioned earlier, there are three main types of biomarkers that are used in ingestible devices: gas, blood, and molecules. Gas molecules include methane, carbon dioxide, and oxygen, and their measurements are used to help diagnose ailments like small intestinal bacterial overgrowth and carbohydrate malabsorption. These gases are the product of chemical reactions in the body, which means it is vital to collect these biomarkers as they are being created so that you can capture what is truly going on in the body. And this is why ingestible devices are so innovative. It's because that they allow for the collection of these biomarkers as they're being created at the source. And blood, specifically heme, is also used as a biomarker to detect intestinal bleeding by monitoring the levels of heme released from red blood cells along the gastrointestinal tract. Ingestible devices allow for this monitoring without the need for endoscopic observations. And lastly, molecules along the gastrointestinal tract, like electrolytes and glucose levels, are collected and used for the early detection of ischemia. And thiosulfate is also collected and used for the detection of intestinal inflammation, and acetylhomoserine lactone, or ACH, is also used for the detection of infectious agents along the gastrointestinal tract.
Thank you, Sir Lawrence. So the thing about ingestible devices is that once they're swallowed, we can no longer see it. And for ingestible devices to be really useful, we want to be able to communicate with it when it's inside the body. To do this, we really need to achieve three things: a wireless communication antenna, a wireless communication protocol, and a power source. And the three aspects are shown in the slide. The first thing we need is to provide enough electrical power to drive our wireless communication system. Historically, battery life has been on the order of a single day to a few days, but this is a rapidly changing field of study. Some researchers are able to harness the acidic environment of the stomach to create a battery. The table in the top right corner shows the power consumption of these devices. And you can see that sleep power mode has a much lower power consumption than continuous mode power mode. And this is very important because we need to use the power budget efficiently by having periodic downtime to save battery. The next two aspects are very related to each other. It's the hardware aspect and the software aspect of communications. We need a physical antenna and a wireless communication protocol. There are many types of antennas, including dipole, coil, and on-chip integrated antennas. It's really up to the application and the end goal. And some designs are capable of higher carrier frequencies and are able to have higher data rates. And the next slide shows how these signals propagate through the body. There are two key informations on this slide. One is that higher carrier frequencies will be attenuated more significantly. Because of this, we can't increase our data rate infinitely. And especially with the limited power budget, we need to prioritize our data. The second key information is that there is a frequency that the device will have the best transmission characteristics. It's important to fine-tune your variables and make it efficient for in vivo use. Because signals are heavily attenuated through the body, it may be beneficial to relay signals from inside to a skin patch, and then from skin patch to controller. So research into signal relay and low-loss communication schemes will allow for faster, more energy efficient, and more accessible connectivity. Next, someone will describe novel materials in ingestible devices.
The third and last focus of the ingestible sensors research is to explore novel biocompatible materials that are used to encapsulate the device. Imagine swallowing batteries, PCB boards, chemicals, or cameras uncovered. The hazardous conditions of the internal pathways of the body present many challenges to the successful operations of the ingestible device. Novel materials can encapsulate vulnerable parts of the device while exposing the data collecting portion of the device to the outside. Size of the pills is the first issue. If the pills are big, there could be more complex functionalities inside the pills, but the risk of device retention is in direct association with device sizes. Capsule retention can lead to GI obstruction, and thus, retention rates of the commercially available non-deformable pills can be a safe standard for ingestible pills before designing materials for the layers of the capsules. Flexibility of the capsules is another critical issue for safety and thus needs proper materials for flexible digital pills. Using PDMS, PLA, or lightly degradable hydrogels integrated on flexible circuits, it could greatly reduce the risk of device retention. Especially the light degradable hydrogels are applicable to different regions in the body, but are especially useful in the GI tract because it allows activation or deactivation of the device through ingestible or endoscopically delivered light sources from Rana's paper.
After exploring all these different aspects, we believe ingestible medical devices have the potential to become the gold standard for non-invasively detecting various illnesses and conditions within the body. We believe the biggest potential lies in using the devices to detect biomarkers for diagnosis, but the biggest challenge to overcome is achieving the optimal device connectivity while also maintaining safety for the patient. The next step for these devices is to transition them from being employed in a hospital or physician setting to being used by the patient in their own home. In order for this to occur and be adopted globally, there must be optimization of the sensor design, cost, and safety. Being cost efficient is key to the adoption because of the scenario that patients must ingest more than one pill. In order to overcome these challenges, our recommendation is that the research done on ingestible devices should shift to focusing on novel materials to develop increased flexibility that will allow for the improvement of both connectivity and safety. If these modifications are added to these devices over the next few years, then we feel very confident that ingestible biomedical devices will become a new normal for patients all over.